Welcome back. After having dedicated ourselves for the last few lectures to doing the mathematics of curves on statistical manifolds, we would like now to go ahead and use some of those ideas to do physics. So we want to do quantum mechanics. Our goal is to study to derive, to reconstruct the theory of quantum mechanics. Now, the usual approach to doing quantum mechanics is that you start with a mathematical formalism, you give priority to a Hilbert space and formulate the whole theory, and then you attach an interpretation to what the formalism might actually mean. And that is a problematic move in that it is not at all clear how to do that, or whether the interpretation is going to be unique or not. In the particular case of quantum mechanics, you have a wide variety of interpretations, none of which are fully satisfactory. Then there is the issue that you give priority to the Hilbert space, and the probabilistic aspects of the theory are sort of relegated to the background. They're meant to help you through some phenomenological rules, like the Born rule, to describe those weird processes that people call measurements. So why should measurements be any different from other physical processes? It's an important question to try to answer, and within the standard quantum mechanical approach, you never get a satisfactory answer. In fact, the best that people have managed to do is to come up with this dual modes of wave function evolution. You have the continuous unitary evolution given by the Schrödinger equation, and then for measurements you have a very different sort of evolution, which is the wave function collapse. Strictly, these two methods, these two forms of wave function evolution, namely unitary and collapse, are incompatible with each other. In other words, the Hilbert space approach and the probabilistic approaches of quantum mechanics, according to the standard approaches, are incompatible and inconsistent with each other. You have to somehow make this decision that, okay, so far so good, the wave function is evolving continuously, and then say, okay, the wave function doesn't obey any longer the Schrödinger equation. Now it's going to be wave function collapse. So that's a problem. Another problem is the actual interpretation of the wave function being sort of like up for grabs. It's not at all obvious what is real in this theory and what is epistemic. There is a certain level of confusion between the two realms. Entropic dynamics solves these problems by going in the opposite direction. We give absolute priority to the probabilities and how we manipulate them. We start with a clear idea of what it is we're talking about, and then we say, but we are uncertain about those variables, positions of particles. We're uncertain about them, and so we're going to introduce probabilities and make sure we sort of update those probabilities according to the information that is deemed to be relevant to the particular problem. The way this ends up being manifested is that there are a number of important distinctions between the entropic dynamics and the standard approach to quantum mechanics. In the standard approach, you really do not know where the probabilities come from, and therefore the indeterminism that arises therefrom is sort of like a mystery that requires to be explained. In the entropic dynamics approach, on the other hand, from the very beginning, we're saying, no, we have incomplete information. The existence of probability is the most natural thing. You don't marvel about that. The question here in entropic dynamics is just the opposite. How is it that in certain special situations, you have the information you have is already sufficient to give you full information about what's going to be happening. That's called the classical limit. How is it that you recover a classical limit where probabilities are no longer necessary? That, however, is a much simpler problem. It's very analogous to the problem of statistical mechanics. You have probabilities in statistical mechanics, but then there are certain thermodynamic limits where you have full deterministic behavior in which you can make deductions as opposed to just probabilistic inferences. In entropic dynamics, the issue of the Born rule is not one that requires a proof or anything. It's the obvious sort of the fact that you're going to have probabilities is like obvious in a theory of inference. What is not so obvious in entropic dynamics is how is it that Hilbert spaces and wave functions and complex numbers arise. So in the standard approach, you start from Hilbert spaces and wave functions. The problem is how do you get probabilities? Here you start with probabilities and the issue is the opposite. How do you get wave functions? Very good. So in order to get this game going, we first start by specifying the model. We are going to say that we deal with particles. Within this model that we're going to be building here, what is ontic, what's real, are the positions of these particles. We could develop the model to deal with fields. That's actually the way, the better way to tackle relativistic problems. Here we're going to be doing non-relativistic problems. But please notice the following. When I say that the positions of the particles are the ontic variables, what's really meant here is that the positions of the particles are the variables that within this model represent something that's meant to be ontic. That does not mean that I believe that the world is made out of particles. Within this virtual reality of this model, theoretical physics is all about models. Reality is something else, something different, something maybe unapproachable, something that we might want to dream about. And we only think that we have a handle on reality when our models are working well. But we never have any proof that the connection between our models and reality is unimpeachable. We can build a model in which the real things, the ontic things, are particles. We can build another model in which the real things are fields. I do not believe that the real world is made out of particles because the model with fields is much better. But this does not eliminate the possibility that there may be other models that do not deal with fields that are even better than these. So the door is open to loops, strings. I think fields are still the better way to go because it's the kind of model with which you can actually make connections to experiment. So let us start. So as I said, we're going to achieve ontological clarity by starting with a clear decision about what is going to be real within this particular virtual reality, within this model. So, the model. We have particles with positions that we're going to label by the letter X. There's going to be 3 coordinates, which we label A, 1, 2, 3, and there is going to be an index N that labels the particle. This particle, we're going to write X or just sometimes I just won't write all the indices. This particle lives in 3-dimensional space. We're going to write it like that, 3D flat space. It is possible to develop the theory in curved spaces. We have done that. but for now we just want to deal with flat space. And there are n particles. Capital N particles. So n goes from 1 to n. And maybe I should say that's for one particle. For n particles, I'm going to write x. X is x1, x2, xn, and this is going to be an element, a point in this n particle space, which is just the product of n copies of the single particle space. Very good. As you can probably appreciate, at this point, we're already deviating from the standard Copenhagen interpretation. These particles have definite positions, which may, however, be unknown. So the positions have definite values. Which are typically unknown. And this is where our first important quantity is going to enter. We're going to be dealing with the probabilities of those positions. So this is, you can, it's worth emphasizing this over and over and over again. The positions are ontic, they're real, and then the probabilities are epistemic. They're not real. There is no need in any of these for quantum probabilities or any quantum theory probability or anything of the sort. It's just standard probability theory. Sum and product rules updated by entropies, and just standard probability theory. Very good. So let us, having said all of this, let us get our model going. Here goes the very first assumption that we're going to make of a physical nature. We want to determine these probabilities in some way, and we have to decide what are the relevant pieces of information that we're going to use to figure out what these probabilities are and how they change. So the very first assumption that we're going to make, and this is probably, well, being at the very beginning, we already made one about the positions being ontic, but being at the very beginning, you probably realize that this is an important one. The particles follow definite trajectories. Particles follow continuous trajectories. Why is this important? The reason this is important is that if you have a continuous trajectory, then it is actually possible to analyze the trajectory by studying what happens in short steps. If you manage to have a law of physics or a law of inference that tells you what happens in a very tiny step, then you can repeat. You can iterate the same rule of inference or the same law of physics to construct the motion. Once you can analyze a finite step, finite motion into infinitesimally short steps, you made a great advance because short steps are easier to compute. In fact, this is exactly what Newton did. The whole reason why we have differential equations in physics is because you can analyze motion or evolution over finite changes in terms of infinitesimal changes described by local derivatives, which then you can integrate. So when I say particles follow continuous trajectories, what I'm doing here is follow Newton. Not so much in saying we're going to find out an equation for the trajectories, but follow Newton in saying we're going to use differential equations to formulate our laws of physics. So that's the big deal here. So we only really need to think about infinitesimally short steps. We need to find the transition probability, from a position x in this n particle configuration space to a neighboring one from x to x prime, which is the original one plus a small increment. If we find the probability distribution for a short step by delta x, then we can just see what is the probability you go from x to x prime. Then you say, okay, given that you are in x prime, figure out how you go to x double prime, and you proceed. So this is how we're going to build the whole dynamics. Okay, so how do we determine this probability? The way we determine the probability to find this transition probability, we use, of course, the method of maximum entropy, and we write there is going to be an entropy. You maximize the entropy of this transition probability relative to a prior, like that, subject to the appropriate constraints. So maximize, nothing new from what we have seen before, right? Just it's a matter of deciding what it is you're talking about, the x's, the new position to which you're going. You maximize, so that this allows us to figure out what the right entropy is. Maximize an entropy subject to given a constraint relative relative to a prior, subject to the appropriate constraints. So here we go. What is the prior? As I said here, we want to figure out what happens when these the particles take short steps. So one of the things that we would like for this prior is that it enforces the fact that if you are at x, you're not going to go very far away. Apart from that, this is a prior. This is the information we have about steps, the information that is common to all steps. Different steps may be different. For example, you take the first step, you are over here. You take the nth step, you're going to be over there, where maybe forces and potentials and things are going to be completely different. Or maybe the motion of one particle later is going to be influenced by all the motions of all the other particles, and the situation, the configuration is going to be different. So what we want to implement in the prior is we want to input information that is common to all short steps, common to all short steps, that implements or enforces short steps. We want this prior here to be such that it gives zero probability if the probability is, or very low probability if the delta x is large, okay? So enforces short steps, and otherwise it's maximally Uninformative. We do not want to be any preferred motion. Principle, the system is here. You do not know if there are external forces, so you want the probability to be the same to go in any direction. You want the system, the evolution to be isotropic, just because at this point in the game, we have no idea where the particle is going to be going. In the same way, you do not know if this particular particle is going to be affected by its neighbors or not. We do not know that. So you do not want correlations or directionality. Maximally uninformative. No correlations. No directionality. Of course, we're gonna, when we actually put, this is all at the level of the prior. When we actually want to compute what the transition probability is, we're going to have to introduce all of that information, right? But right now, we want something that's common to all steps, enforces short steps, and otherwise it doesn't tell you anything. So let's determine the prior by using maximum entropy. We can do that. We're going to use maximum entropy itself to find Q, the probability that the system of n particles jumps from x to x prime. And so we're going to do an entropy relative to some underlying measure. And here we're going to have the probability log relative to the underlying measure. I'll just write it like that. So as I said, we're dealing here with a flat space, and I have no idea, maximally uninformative. I have no idea where this particle is going to jump. So I'm going to pick the prior here to be uniform. I'm using Cartesian coordinates, so this is just a constant. I can forget about it. Very good. How about, what else do we want here? Well, we want a prior that does not introduce correlations. So if this is uniform, there are no correlations there. So what I'm going to just impose is each particle moves by a little bit. So we're going to impose for each particle we're going to impose that there is a constraint and here I'm going to put the metric for flat Euclidean space, and this says, using Pythagoras theorem, that the expected value of the distance is some quantity what we're going to call kappa, and we're going to have different constants here for different particles. So this is some quantity. I don't really need to worry too much about what it is, except that this quantity is very small. These different particles may jump by different amounts, so that's why I have an n there. And I have n of these constraints, one for each particle. Very good. What do we have from here? We have a uniform prior for this Q, and we have a quadratic constraint. Go ahead and maximize this entropy, and what of course you're going to find out if the constraint is quadratic is that I'll just write it here. Conclusion. And of course, beyond this, there is another constraint on normalization. So what this says is that what we're going to have is this is uniform, no correlations. This is one of these for each particle. It's spherically symmetric. And so there is going to be one Lagrange multiplier for each one of these particles. and we want this to be, it's going to be spherically symmetric, and you can, and we want to sum over all the ends, because we have n of these constraints. And furthermore, we want this to be to describe short steps. So we're going to put a minus sign here. And require that alpha n be large, well, be positive and large. For convenience, for later convenience, it's good to introduce a 1/2 there, and the only reason I introduce a 1/2 there, which just amounts to rescaling the Lagrange multiplier, is that you can see that this is a Gaussian. Gaussians do not have correlations between the various degrees of freedom, and so this satisfies all our requirements. Enforces short steps, because if alpha is large, then any large displacement will lead to zero probability, or very low probability. And there are no correlations. That's because it's a product of probability distributions, so they're all independent. Very good. We have our prior. Eventually, to make the steps like really short, we're going to make it large, and eventually we want these alphas to tend to infinity. The particles need not be identical. Different particles may jump by different amounts. We're going to see later how we choose these alphas. Now, how about this very small quantity that we have here? Well, just compute this quantity here, and you can figure out what the kappa sub n is in terms of the alpha sub n. They're like inversely proportional to each other. So basically, kappa being small is alpha being large. Okay, so now that we have the prior that goes here, let us focus on the constraints that we want our transition probability to satisfy. And these constraints are what specifies a good chunk of the physical information. When you have a Lagrangian, there is a certain amount of the mathematical formalism that is the same for everybody. It's a Lagrangian, Hamilton's equation. It's the same for everybody. But when you have a Lagrangian, there are certain aspects that may be specific to the problem, namely, what are the potentials that you're putting there? The forces are going to be different for different problems. In the same way, our constraints here are going to be different for different problems. And so this is where we're putting the specific physical information for our problem. We just said here that the prior was designed to introduce no correlations and no directionality. Well, one of the things we want to introduce into a problem is the idea that sometimes particles move in one direction, right? If you just were to have this prior and figure out what dynamics it induces, it's sort of like an isotropic diffusion. It's pretty boring. You start with something localized and it just diffuses out. So what we would like to do is introduce directionality, and also we would like to introduce correlations between the particles. So that's going to be crucial, because at some point we want entanglement and all sorts of things. So let us introduce a constraint that does that. So the first constraint is something that introduces correlations and directionality, the drift constraint. Well, okay, I'll call it the quantity that we introduce here. We call it the drift potential. The idea is the following. If it were just something that gives you, like the prior, an isotropic diffusion, like in a Brownian motion, things just diffuse out. How do you make sure that all of this diffusion is going in one direction? Well, you impose a potential of some type. You can impose, say, an electric field that will push the particles in one direction, or you can impose a gravitational field that will make the particles diffuse in a preferred direction, down. So what we're going to do is exactly the same thing. We're going to introduce a quantity, the drift potential, the drift potential, and we're going to say there is a constraint, a single constraint in configuration space. Notice that this x is in configuration space. It includes the positions x1, x2, x3, xn, all of them, right? So this is the drift potential, and we're going to write a constraint in terms of this object here. We would like to talk about how one of these guys, the expected value, we want to impose a constraint on the expected displacement. And because this is supposed to be like a scalar function, we're going to write this as being the gradient of this scalar function. And this is going to be another small quantity. Very good. Where does this come from? Oh my God. What on earth is this drift potential? Oh, by the way, another way to write this is to say that the change, if you were to figure out how the drift potential changes when you go from x to x plus delta x, the change when you take the expected value is exactly the expression we have there. So this is a clever way of writing the constraint. The change of this quantity is small. But where does this drift potential come from? Okay. There are two ways to think about it. One of them, or rather three ways to think about it. A don't ask, don't tell policy. You don't need to know where it comes from. This is the constraint. End of story. Now, this seems like a little bit too drastic, and it's going to make you think like I'm cheating. But consider the alternatives. Or rather, let me put it this way. When, for example, Newton came up with the theory of gravity, he said there is going to be a force that deviates the particles from inertial straight line motion. There is going to be a force, and I'm going to say that this force acts in real space, and I'm going to say that it is inversely proportional to the square of the distance to the sun, to the origin of the force. And at no moment he actually says why or what is this force. He just said it's what it is. Trust me, if you make this simple assumption, if you make this single assumption of a force, you can explain the motions of the planets, of the moon, why things fall on Earth, why there are tides. You can explain a lot of things on the basis of a single assumption. So that's why there is value in saying, instead of making many assumptions to describe many different phenomena, I make a single assumption and describe many phenomena that in principle could be disconnected. With the same phase, we can describe entanglement, superposition, tunneling. We can describe the energy levels of hydrogen. We can do a lot of things. So with a single assumption, we can describe and unify many different phenomena. So that's the first answer. Don't ask, don't tell. It works. Let's proceed. Later we will worry. Okay, a little bit later we will worry. And so one of the things that you may want to know is, Well, in the case of Brownian motion, it was an electric field. Is there, for certain systems, situations where we might actually know what this drift potential is? Actually, that may be the case when it is possible to actually give an interpretation of this drift potential in certain cases as being the entropy of some other variables. So that when I say that these particles X want to evolve in the direction of the gradient of something, they're going in the direction of maximizing somebody else's entropy. So it is possible to define entropic dynamics in which this phi, this drift potential, is interpreted as an entropy. So that's explanation 2. Then there is a third explanation that I find particularly convincing, even though it is a little bit too mathematical. And the idea is we want a flow, an evolution of rho. The most natural thing to do if you have a space of probability distributions is to consider the cotangent spaces, consider the cotangent bundle in order to define a momentum on the cotangent bundle and at some point introduce a symmetries such as symplectic forms, symplectic structures. We want a flow of rho. It is natural to introduce a momentum conjugate to rho, and this momentum is phi. So for each rho x, we introduce a phi x. This explanation of why we introduce a phi is an explanation that is motivated very much by the maximum entropy idea that if you want to describe the changes in probabilities, you're going to need constraints. Some quantity describing a constraint is going to be necessary, so we introduce it. Furthermore, the choice of those constraints is going to be guided or even determined by various symmetry principles that apply to our problem. Crucially, the symmetry principles are going to be the preservation of certain symplectic structures, geometric structures, spherical symmetries, things like that. So this is why this phi enters the picture. It's a momentum. Very good. We have a first constraint there. Just with this, we can actually build an interesting dynamics. But I'm going to introduce yet another constraint to make it even look more like physics. I'm going to introduce a gauge constraint. A gauge symmetry constraint that we eventually, not now, but later we're going to identify as being responsible for how the particles react to external electromagnetic fields. And the way we're going to introduce this constraint is to say, look, this is a constraint that also affects the motion of the particles. So it is a constraint that affects the delta x, the displacements. Now, there's a big difference between the previous constraint and this constraint. Here, this was a single constraint. So this is a single constraint. One constraint for all particles. A single constraint. This is what this allows this to be introduced correlations, because this is this x here that appears here. this x is x1, x2, xn, and so the motion of one particle is affected by the motion of all the others. Here, of course, I forgot. Of course, we're summing over a's, just the usual Einstein convention. And then here we're summing over all the particles as well. Oh yeah, my previous remark that this was the change in phi must have confused you. It's only when I sum over all that I get this constraint. Very good. Here, however, we're going to say this is for each particle we have n constraints. So one constraint. So this is one constraint for each particle. We're not summing over n, and I'm going to say that there is an external field that, of course, we're going to identify with a vector potential at some point. We're going to say there is an external vector field, 3 components, and there is only one of them, and this, of course, acts on the location of the particle, and this is going to be another small quantity. And I believe we are done. Let me maximize this entropy subject to normalization relative to this prior, the Gaussian that I wrote down here, and with these 2 constraints on displacements. And the result is, so this is the transition probability. The result is there is a normalization, then there is the prior, summing over all n particles, alpha n over 2. Then there is the Gaussian for the prior. And then need to go to the next line. Then there is minus a Lagrange multiplier that goes with the displacement n, and the first constraint there is a sum displacement gradient. So we have the sum displacement gradient. Phi. That's the first constraint. And now we're going to write the second constraint. The second constraint involves its n constraints. That means that each one of these requires its own Lagrange multiplier, and then it's going to involve in the exponent, it's going to have the delta x and the a. So then I'm going to write here one Lagrange multiplier for each constraint. Then there is the delta x, and then there is the a evaluated at the location n, close parenthesis, and close parenthesis. The Lagrange multipliers that you see here are of 3 types. One is alpha n. It is the Lagrange multiplier that's supposed to be large and enforces short steps, and that comes from the prior. It's the Lagrange multiplier that determines the prior. Then I have another Lagrange multiplier, alpha prime, that calibrates the response to the drift potential. And finally, I have another Lagrange multiplier, which is the product, alpha prime beta sub n, that calibrates the strength of the response to this external potential. That at this point, we do not know what it is. It's just an external potential. Very good. It is convenient to write this, the alpha prime, beta, and beta separate, because then I can see that this factors out. And we have a quadratic term. We have a linear term. we can actually rewrite this by completing the squares. So here, let me see, the alpha n, alpha prime, beta n are Lagrange multipliers. And now I'm going to complete the square and write this probability distribution in a somewhat simpler way. And the distribution now is going to look like this. There's going to be a minus, there is going to be a sum, there is an alpha n over 2, there is a delta AB, this is the metric for the three-dimensional space, and then we're going to have the product of delta x and A minus some quantity that I'm going to call bar, multiplied by another quantity B with delta B there. And all of this, of course, is summed over A, summed over B, so that here you have like the scalar product of those two. The first term, delta XA, delta XB, reproduces the prior, and the cross terms reproduce this term here that's linear in delta x, while the last term, the delta x bar, this is something that is just, these are just constants that are independent of x prime. So I can actually absorb that into the normalization constant. Maybe I should have called it with a different name. So maybe I should put a prime there. And so this is a different z, a different normalization. So what is this constant here? It's just a matter of completing the squares. The product of the first with the first gives you that. The cross products give you the second one that allows us to write out where the displacement can be written as an average quantity delta x. So let me write the average displacement is this quantity xb, and which is equal to, where do I have it? It's alpha prime over alpha n, the n a phi minus beta a x n. So this quantity delta x bar is just the part that comes from the two constraints. You can see here that a typical displacement, the typical generic displacement, the generic delta and x is now written as, let me rewrite it, as the average which is this delta x bar that I wrote here, plus a fluctuation. Let me write it like that. So this is called the drift, or average drift, or expected drift, and these are called the fluctuations. You can see that the quantity that appears up here is this fluctuation. So what we have here is the exponential of minus alpha delta w squared. So it's typically a Gaussian in the fluctuations, where I already written down what the drift is, and the fluctuations have this property that the average fluctuation is going to be 0, and you can see that from here. If you take the average is going to be, this is a constant, so the average of the average is itself. This equals that. Whatever that is has to vanish in average. And the actual fluctuations then are given by the correlation function. And it's a matter of computing from here. And it's just going to be 1 over alpha n. This n and n here are the same. So there is a delta n prime. If I put a prime here, that makes it neater. And delta a b. So here we are. We're done. We finished. We have the whole thing under control. Given these expressions here, where we have the alphas and betas and everything, we can, if we want, we can go back and figure out what the kappas are, what these constraint functions are. But the fact is that just as in statistical mechanics, you don't have to specify what the expected value of the energy is. It's much, much easier to specify what the Lagrange multiplier, the temperature, beta, are, right? So in the same way, we do not need to specify the actual constraints. We specify the Lagrange multipliers, the alpha n, the alpha prime, and the beta n. Very good. Before it's time to stop here, what I would like to point out is that there are two remarks here that are important already at this level. Remark 1. The way the whole theory has been set up is that I am asking from the very beginning, I am asking what is the transition probability from one position to the next in a short step, but from one position to the next. And when you look at the constraints that I have used here, the prior is again from that position to the next. These constraints involve delta x, which is one position from x to x prime. So the interesting feature that we are already seeing appear here is that px prime does not involve any information about x's positions prior to x. In other words, the information that we have imposed in order to find x prime depends only on the x and not on anything prior to x. The prior history of the system is not relevant. We are assuming that all the information we need in order to figure out how the system moves from x elsewhere is contained here at this instant. I still don't want to use temporal language, but it's kind of difficult to say that without worrying about anything else that happened before. In other words, we have information from the point x onwards, and we do not need information about the trajectory before x. What this implicitly immediately implies is that entropic dynamics is described by a Markov process in which the future evolution is independent of the past. It depends just on the present and not on the past. Very good. The second remark. Another feature that we see emerging already from the nature of the constraints. You probably realize that here the first constraint that we're using involves displacements. The second constraint involves displacements. So what this means is that these two constraints are not completely independent of each other. I could increase or change this function, this drift potential phi, by a certain amount, while correspondingly decrease or change those guys there to obtain the same final transition probability. And indeed, this is what we see here when we have this function here, this probability, transition probability. The quantity that regulates the transition probability is not the drift potential by itself or this vector potential by itself, but a peculiar combination of the two. You could increase this first term by a certain amount and decrease this term by a different amount, by the same amount, increase and decrease, so that the whole thing remains fixed and the probability is the same. You can see that also at the level of the expected displacement. It depends not on phi alone or A alone, but on a combination of the two. So again, it is possible to change the phase of the wave function while changing the external vector potential in such a way that the motion remains the same. When you say it in this way, you see that immediately the constraints have been concocted in such a way as to recover a gauge symmetry. Remark, both constraints, the gauge constraint, drift, and the gauge constraint, the electromagnetic constraint, are not independent. They depend on the gradient of phi minus beta A. So what this implies is that there is a gauge symmetry. You can change phi by a function and change A by the gradient of that function, and you still obtain the same motion. So it's actually kind of fun to see how it is that different aspects of quantum mechanics start emerging as we introduce each one of these features. Very good. We have reached here a certain level of completion. We know what happens in a short step. That's it. This is it. It's still given by these Gaussian distributions. Alpha is large. What we would like to do next is we want to iterate these we would like to iterate this transition, this evolution, to form, to find the distribution at the next instant. If I give you the probability distribution at a particular instant in time, I would like to evolve it according to this transition probability to find the probability distribution at the next instant in time, and then repeat, iterate this as you go along. What we're going to do in next class is figure out where this equation comes from, how we obtain it, and how we actually implement this iterative process, this integration in a clever way. That's for next time. See you then.